Alright, now I'm going to use this definition of the delta function to prove the Fourier theorem, which states that if you take a function f and you perform the Fourier transform as I've defined it up here, then you can recover the original function f by performing the inverse Fourier transform as I've defined it here. Do you or do you not? Let's check. Alright, so do you or do you not recover f if you perform the Fourier transformation and then multiply by e I omega t and integrate over omega to perform the inverse Fourier transformation and divide by 1 on 2 pi? Well, this integral can be combined into a double integral. And I can combine these two exponential factors together, and I can switch the order of integration as long as omega and s both still range from negative to positive infinity. Now here's the trick. I'm going to put in this fudge factor of e to the negative omega squared on 4k. But I'm going to take the limit as k tends towards infinity. So as k grows larger and larger without bound, the fudge factor becomes closer and closer to unity, and it shouldn't affect my final answer. Why on earth would I want to do something like that? This is why. Because if I perform completion of the square on this exponential term, this is what I get. Let's check. If I have two terms and I square it, I get the square of this term with the minus sign, and I get the square of this term, which I'm compensating for, keeping in mind that I squared is equal to negative 1. And I also get a cross term, which is 2 times this times this. So 2 times this, and here we have it. So I can take this and use that as the exponential factor. And I can split it up into two pieces, e to the power of this piece and e to the power of this piece. And I'm ready to do my integration over omega, because there is only one term, one factor that depends on omega, and this one is it. So the integration over omega really is just the Gaussian integral, which I introduced first up. Except instead of e to the negative t squared, I've got e to the negative omega on 2k minus ik t minus s squared. So if I just perform a change of a variable, then instead of root pi, I get 2k times root pi. The other factors, the f of s and the e to the negative t minus s squared k squared, they don't depend on omega, so they can be moved out of the integration symbol. And this is what I've got. The 2 here cancels with this 2. And the root pi here partially cancels with the pi in the denominator here. Well, hang on a second. This looks very familiar. The limit as k tends towards infinity of k times e to the negative t minus s squared k squared divided by root pi. And indeed it is. So, this here is nothing more than the delta function of t minus s multiplied to this function f of s, integrated from negative infinity to positive infinity over s. And according to the property of the delta function, which I proved just a moment ago, this integral is equal to f of t. So there you have it, the Fourier theorem.